So I'm going to talk about cascades and social influence on networks. So this is very different from the stuff that I did as a PhD student, although dynamical systems are involved, which for those of you who remember my interest will not be surprised by that. Various collaborators will show up on some of the papers that I have there. And what I really want to do is to try to get you interested in this family of problems. If you are interested in it, get you more interested in it, and if you're not yet interested in it, get you interested in it, as something that's a really nice playground for applied mathematicians to study. Let me just use that. Okay, so I'll give a bit of an introduction, but then this modeling social influence is really part of the introduction. And then I'm going to define a new dynamical system that we define that generalizes some others that exist in this we call multi-stage complex contagions. And this is from a paper that just got accepted today, just got the notice this morning. I'll have a bit of an interlude because there's some interesting issues of when certain approximations are good and when they're not good, and there's some open problems there independent of the modeling of social influence that are also, I think, very interesting, or will be very interesting to people in this room. I'm going to then after that I'll go back to some analytics for this. So this is kind of interrupting the story in the middle, but I think it's doing it at a useful point to do it. I'll briefly talk about one more general thing that we've done, and then I'll also very briefly talk about one that actually brings in data a little bit more seriously, but has some of a similar vein. And then I'll summarize. Okay, so one thing that's going to be familiar to all of you is to look at ODEs and PDEs. And if you think of a toy model for a biological epidemic, but I could have put a toy model for something else. So this is the susceptible, infected, recovered, or removed model, depending on whether you're violent or not. And it looks like this, and I can have other models that are similar to that. And one of the things that will happen is that you have a well-mixed. It's assuming it's sort of well-mixed, right? There's no space that's in there. People are interacting with each other, and just by virtue of existing in the same place, infections are somehow passing through. So it's interesting to study, and you can do some math with it. But there's something that's missing. So one way to add space, you can add it as patches. People have done that a lot, or you can add it as diffusion terms, and then you can get a nonlinear PDE, and you can study waves of diseases going through. And this is all very familiar, but in the last, especially 15 years or so, people have instead put some spatial dependence in via dynamics on networks. So thinking about who is actually contacting whom, and using that to think about how different processes are moving along. And so you incorporate which people are interacting with each other people, say, if you're thinking about a social network, so the people are what are called nodes, and the ties are what are called edges. So nodes are vertices, edges, or links. And so this will yield a dynamical system on a network, and you can do various types of it. And I'll actually consider social epidemics, but you could do a biological epidemic and so on. And the basic question that one might consider, and there's various flavors of it, is how does the network structure affect the dynamics on top of it? And the reason you can do vice versa, you imagine that if somebody is sick, they might stay home, and that will affect the structure itself. So in this talk, I'm only going to think about how does structure affect dynamics, but you can go in the reverse, and it's very interesting to go in the reverse. Okay, so why bother? Okay, the short answer is that it's interesting. That's the only one that I really care about, to be honest. But get interesting and tractable examples to study effects of the network structure. And these various cascade models are a nice playground to try to do these things. Now, in the real world, so as some of you at least, the faculty will have heard Rick Durrett say that the real world is a nice place to visit. So I'm kind of taking that approach to this talk. We also want to think about simple contagions, or what can be called simple contagions, versus complex contagions. And the way that I'm using that terminology is that a simple contagion is something where, at least to a reasonable approximation, I can think of it being transferred from one person to another. Now, I know that's not completely true for diseases, but let's assume it's true. What I mean by a complex contagion is that I really want to think about the transfer possibly occurring from multiple people to me. So I'm looking at who's influencing me, and that's going to cause a transfer, and I cannot just say, oh, this idea went from one person to another. Right? At least that's the way that I like to use the term. So the first time I saw this term, and it was from work by Santola and Macy, actually, I think it's a 2007 paper, I'm not sure which paper, but David Santola has continued doing this stuff on the experimental side. He's actually designed some nice experiments where he puts a graph of a specific structure into the system so that you have, it's almost like a physical laboratory the way you're used to it. And so instead of having a real social network, you have an artificially generated social network, and then you can have more of a comparison between the mathematical side. So these plots come from there. I just wanted to illustrate that paper as a nice place to start motivating some of this. You can also think more directly about social movements. You might think about mass movements. You might think about memes that go on a place like Facebook or Twitter. You might think about adoption of Facebook apps, which is in the sort of Cambrian era of Facebook of 2007. You might think of social and biological epidemics on networks. Okay. Various challenging. So let's suppose you see something that might be a social contagion. It looks like a social contagion. When the UK had riots a couple of years ago, if you look in the newspapers and online, they're like, oh, there's a social contagion. Okay, well, maybe, right? So and then there's a well-known series of studies by Fowler and Christakis, starting with obesity and going through smoking and various other things with empirical data. But it's very difficult in general to distinguish from a few possibilities. One is that you really might have social influence spread going on. You really might have that. Another thing that might happen is that you might have homophily, namely that people are doing things because they're inherently similar, and it might be that one adopts it later, but it might not be an actual transfer of the idea from one person to another. They might just be similar in some way. Or it could be the environment, so covariates. So covariates is a statistical word for everything else. You might have a common external influence instead of a common internal influence. So in the example of obesity spreading, maybe more McDonald's opens up is the type of thing that you might consider as a common external influence. But it's not an inherent similarity of people. And if one were going to do, okay, I guess the word control strategy is a little bit insidious in this application. But if you were going to do some sort of legislation, if there was some behavior you didn't want or you did want, and you want to encourage it or discourage it, what is coming from which of these is probably going to have an influence on what legislation that you write. So you do want to do this. Okay, so then, given that one might want to do this, so how do you gain insights on it? So one thing you can do is well-controlled experiments in principle, and careful data analysis and lots of statistics. And I think that the majority of the work on these topics tends to take this approach. I think that's the majority of it. The approach that I want to advocate, not as replacing it, but as supplementing it, and is one that's particularly suited for people with CAM types of skills, is more of a forward approach, where you get some simple, tractable, generative models that you can study mathematically, do bifurcation diagrams, and so on, and try to ask the question, what is the simplest model that can give me this behavior? And eventually what you want to do is to combine something like that with the statistics and with the data analysis, and when possible, with the experiments. So when I say experiments, I mean like the Damon Santola one, right? I don't necessarily mean a full social network where you want to do observations as well. I mean one like his, where he engineered the actual network, and it really is like an experiment. And I think the experiment really becomes an appropriate word in the social sciences, and that's, it's nice to see that. Okay. Another more general goal is you could say, I want to advance models of social influence, develop new generative models, combine them with this, and so on. And the success of models of biological epidemics, where you have simple equations, but you also have actual estimation of parameter values from real data, is something that in this sort of field that one can strive for, and that would be something that would be really nice to see more of. Okay, so there's a Watts model, not the Watts-Strogatz model, but the Watts model. So Duncan was here. He left Cornell right before I got here, actually. He has a paper in PNAS in 2002, which has a model as follows. There's also older models from people like de Groot and Granovetter from the 70s, and from Noah Friedkin and so on. Okay, so let's suppose you have some network, people are connected in some way. Unweighted edges, for example, although that's not a requirement in principle. So each node has some threshold, which you draw from some distribution, and each node is in one of two states. They are 0 if they have not adopted the idea, and they are 1 if they have adopted the idea. And then you choose some seed fraction of nodes. I think Watts' paper, he chose 1 node, but then the seed fraction would change depending on the side of the network. So choose some fraction of the people to have this. You could do it uniformly at random or some other way. You might start in a specific spot if you want to try to spread a rumor and figure out where you should start the rumor. And initially that one will be in state 1, so infected, active, and so on. And in this particular model, if you adopt something and go from 0 to 1, you cannot unadopt it. So it's monotonic in the sense that you cannot go from 1 to 0. And there are certain theories that one can use that actually require that assumption. And then in general, one can generalize it. Okay. If you're implementing this on the computer, there's 2 types of updating that can occur, and you sometimes have to worry about whether they give you different behavior. So synchronous updating would be a discrete time updating where all nodes get updated at once. And asynchronous updating would be a continuous time updating where you would update some fraction of nodes in a time step. So you could do what would be called a Gillespie or kinetic Monte Carlo if you're actually simulating it. This can lead to very long simulation times, by the way. In many cases, the equilibrium behavior will be the same, but not always. And the time-dependent behavior will have some differences. Okay, so the particular update rule, so this threshold model versus some others will have a particular update rule. I compare the fraction of infected neighbors. So kj is my degree, how many friends I have. M is how many neighbors have 1 already. And I compare that to my threshold, and then I become infected the next time I'm updated if this has above my threshold, and otherwise no change. And an important variant is that instead of looking at the fraction of infected neighbors, I look at the number, and the difference that will arise, and this difference will actually have an impact not only on the application, but even on when some hypotheses of theories are valid, is that so this one will give no credit for, the top one will give no credit for having a high degree, for having lots of friends. Right? If I only care about the number of active neighbors, then if I have a lot of friends, all else equal, I'm more likely to have active friends as well. So do you care about how many little blips of feeding things that you get on Facebook, or do you care about what fraction of your friends do? And depending on what problem you're studying, one or the other might be more relevant. But sometimes they do lead to different things in the mathematical side, so it's not necessarily a matter of an arbitrary choice. And then the monotonicity in this sense is that nodes are always staying at 1. Okay, so this slide, before I forget, I stole from my former postdoc and my co-author Sergey Melnik. The slides that have neat writing and so on that look like they were copied and pasted come from him, just to give him the credit for that. Okay, so we're going to use the terminology of response function. As far as I can tell, my collaborator James Gleeson was the one who started using that in this particular framework for the dynamics on networks. So nodes have binary states, and I'm going to start giving them labels because that will be convenient for some stuff later. So a node that is in S0 is inactive, so it's not influencing neighbors. A node that is in S1 is active, it is influencing neighbors. And then at each time step, I'm again going to become active if some fraction exceeds a threshold, or some number in the other case. But I can actually write it as a response function, and the reason I want to do this is that other functions like bond percolation and K-coorganization and a few other things can also be written like this as a response function, just with a different choice of function. And then when you start deriving the theories, you do it for response functions that satisfy certain properties, and you can get a few different ones of them. So even though I'm focusing on the social influence in this talk, there are certain aspects that are more general. And so this response function will basically describe the probability that a node of a given degree, so here I'm separating it by degree class, but I could have in principle separated by something else, will become active as long as this many of its neighbors are active. Okay, make sense so far? All right. So one of the things that you can do is study equilibrium. I can let time go to infinity, either continuous or discrete time, and say, given a certain initial condition, what fraction of the nodes eventually become active or inactive, and you can start asking the question, where should I start a rumor in the network to get it to spread to the most, or spread the fastest, or whatever. So if I started here, for example, so everything has the same threshold in this particular example. So if I started here, everybody becomes active eventually. If I started here, this fraction become active. If I started here, this fraction become active. And then in general, if I were going to do things and not specify an initial condition, I would average over many realizations where I would consider different initial conditions. But there are versions of this problem where you really want to think about where should I start a rumor. Okay, so a schematic for the Watts model is that if I'm below the threshold, I'm not influencing anybody. But whether I'm barely above my threshold or strongly above my threshold, I'm influencing other people in the same way. Okay, But in real life, you have people who are fanatics, and maybe they exert more influence. So you could generalize this model so that you go and have fanatics, and so that would give a schematic like this. I was really pleased that the paper got accepted this morning, so I decided to put it there again. In any event, so now what we do is if you're above, you have a second threshold, right? So you've got one threshold that's drawn from some distribution that says, I now adopt this thing. You have another threshold which must be at least as high as the first, such that not only do I adopt it, but I'm going to tell all my friends about it and try to influence everybody and so on. S2 is a subset of S1, okay? You don't have to formulate it that way, but we chose to do it. S1 is not a subset of S9. It's not obvious from this picture, and it's something that we had to put carefully in the caption. Okay, so types of nodes. I made this slide for a presentation this summer. It's one of my favorite ones ever. Anyway, you've got passive nodes who exert no influence, represented by this guy, the dude. You've got active nodes who will influence neighbors, and you've got hyperactive nodes whose name was partly chosen so that I could make Spaceballs references in talks like this, which influences neighbors with a bonus influence compared to active nodes. So S2 is a subset of S1, but S1 is not a subset of S0. And the very interesting thing that occurs with this particular model and having this extra stage is that because you have two transitions, you can think about the different time scales of transitioning from 0 to 1 and 1 to 2, and you need the third stage to start thinking about the competition of that time scale. So I would argue that this is among the simplest models in which you can start actually thinking about that type of competition. So that's what mathematically one of the things that I find really interesting about it. And so I think that the jump from 2 to 3 allows you in principle to then start going to 4 and so on if you want to add more bells and whistles. Okay, so we're gonna use a notion of peer pressure and go back to our response function. So every node is going to experience some peer pressure, and we're dividing it by degree class, which is a completely arbitrary thing. You could divide it by betweenness or whatever else, but this is maybe the simplest way to do it. And so you get M1 influence from the number of neighbors in S1. You have M1 neighbors in S1, and then you have M2 neighbors in S2, and you get M1 plus beta M2 influence. They still have their influence from being in M1, but then they have this bonus influence. And I'm going to divide it by the number of neighbors I have. So this is what I'll choose for my peer pressure, and if you don't like it, you can just do the same thing with a different function, and away you go. And beta is the bonus influence. So if it's 0, then I reduce to the previous model. Okay, and then the update step says a node J will become SI active if the peer pressure it experiences is above its threshold. So each node has 2 thresholds. The second threshold is at least as large as the first, and they're chosen from some distributions. Now, if you chose the thresholds, if you had the same thresholds, then you would write the response function this way, and then you can take this and write the response function for that if you want. Okay, so what can happen? Well, one of the things that can happen, well, everything that can happen in the Watts model can also happen, or the Centola-Macy model if you choose to do number rather than fraction. Cascades of S2 can derive cascades of S1. So adding bonus influence can allow cascades to occur that might not otherwise occur. And then that's intuitively, it's built into the model, basically, but it's nice to see that it can happen. And so this particular example, if I have this R1.5, R2.3, 2% of the nodes, or about 2%, are initially S1 active. The data that this was used on, so this was used on a real network. It's a Facebook network, this time from the pre-Cambrian era, not the Cambrian era, so 2005, when Facebook was university only, and this is the entire network of friendships from University of Oklahoma from then. So it's there's a binary connection, and 2 people are connected if they have a Facebook friendship. So this is about 18,000 nodes in the largest connected component. The reason I wanted to use this data, there's a couple reasons I wanted to use the data set. One is that I have 100 different ones of those, and so it's nice because it gives me 100 parallel things to try. Another is that it's the type of network where you can at least imagine a rumor or idea propagating on. So there's some element of, quasi-reality in it or something. In any event, activations don't spread under the Watts model, whereas if I have the second threshold and allow bonus influence, I do eventually get spreading this top part is the fraction who adopted equilibrium, averaging over some number of realizations. Okay, less intuitive, but something that can also occur, is that by adding sheep, I can get cascades when I would otherwise not get that. There exist regions in the parameter plane for which this happens, and I think it's not obvious in advance that that would occur. And I think that if you tried doing a different multi-stage model, it would not necessarily be true that another multi-stage model would do that. And I don't know. But anyway, so this one's more interesting than the other one. So in this case, I have there's a single stage case. So the S1 dynamics relates to the S2 dynamics. And the second case, I lower the first threshold, so I add more sheep, and all of a sudden, I get cascades. Okay. And I'm not saying that this usually occurs, just that there exist parameter values that have non-zero measures for which it occurs. I think it was, 10% of the parameter values, 4%. In the paper, we say more specifically what fraction parameter values. Okay, so we've seen this on real networks, but the real networks are a little bit harder to control in terms of how the transitions are occurring. So one thing that's very useful is to come up with synthetic models or synthetic ensembles for which you have more of a control of what's going on. And a particularly useful one that we've done in this paper that we've used before, but I've never seen given a name, and we felt it was useful enough that we gave it a name. So we call it Z1, Z2 regular random graphs. There's something called a Z regular random graph that says every node has 6 friends, and otherwise they're connected at random. So here I say there's 2 types of pieces. One type of person with Z1 friends, one type of person with Z2 friends, and I connect them at random, and I can either do this in an uncorrelated way, or I can specify a sort of homophily or assortativity type term to specify how often a Z2 should connect to another Z2 versus a Z1. So I'm going to fix the degree distribution, and in this particular case, I will also fix the joint degree distribution, and otherwise I will connect uniformly at random. So, for example, I might say, half the nodes are losers and have 4 friends, and the other half are cool people who have 24 friends, and then I have some notion of how often nodes of this type and nodes of that type connect to each other. Right. So consider an ensemble in which each node has on average all but one neighbor from its own class. I'm going to assume some identical thresholds, and let's consider the case in which S2 activations drive S1 activations. And the point of doing this particular thing is that you can track separately when these guys transition and when those guys transition. Okay, so what we have here, now this is time. This is the fraction of the nodes that have adopted. This is averaged over some number of realizations. Again, I don't remember what number it is. And if we look at the S1 transitions, so you have an overall S1 in this case. So these are your 2 thresholds. The second threshold is much higher than the first. You'll notice that the degree 4, that all the transitions are actually occurring only from degree 4 nodes, and the degree 24 nodes are never actually becoming even S1 active. This is with no bonus. Oh, of course it doesn't become, it becomes no bonus. Okay, if I add bonus, here's a particular amount of bonus that happened to give me something interesting. I have both the degree 4, I have degree 4 nodes becoming S1 active, degree 4 nodes becoming S2 active, and then the degree 24 nodes become later on. So if I look at the overall S1, I get this, but in fact I can separate it by the different types of nodes to track separately when these things are occurring. Okay, so you can do some numerics, but we also want to do some analytics. If I were not going to do analytics, it would be still useful, but maybe not quite as useful to have something synthetic like this instead of an actual social network. So now let's consider uncorrelated ones, and the reason I'm doing that is that the analytics are harder if you do the correlated one, but at least in principle you can do it. So now I'm going to fix a degree distribution, so I know how many degree 4 nodes there are, and I know how many degree 24 nodes there are, but I'm no longer fixing how they're mixing together. And I'll connect the stubs uniformly at random, so now this becomes a special case of what's known as a configuration model, just because of this particular degree distribution. And you can derive, and I'll give you at least some hint under the hood, of how to get some analytical expressions for the final fraction of those types of nodes and those types of nodes. And you can even derive some analytics for the time evolution. The analytical approach is going to use what's called a tree-based mean field theory, so I'm going to need to explain those words. And what it's going to assume, it's going to take several slides to explain those words, is locally tree-like. And it's going to ignore structural correlations, and it's going to ignore dynamical correlations. And the 2 papers to look in, at least the 2 of ours to look in, this paper from 2011 and I'll show you, you'll love the title of it when I show it to you, is about locally tree-like. And this paper from 2012 is about mean field. And these are basically saying, trying to explore when these things are really valid, because there's this interesting phenomenon that those people who do asymptotics have seen, that the results seem to be valid even in many cases when the hypotheses that led you to derive the results are horribly violated. So there are deeper mathematical theories that people, to my knowledge, have not yet done to find out when are these things actually valid. And that's one of the things I hope some of you will be interested in, and I'll give you more details on that. Okay, so let me give you a hint of the analytical approach in the next couple slides, and then back up again to locally tree-like. Okay, so let's consider the single stage case. So I'm going to consider the Watts model. So the advantage of doing this, so it's intuitive, you can generalize it to other cascade type problems, and so the nice thing there is by writing as a response function, just saying this theory works for response functions that satisfy certain conditions, then you don't just get this for the Watts model, but you also get it for percolation and a few other things. It's going to have to be monotonic. Okay, so remember, S2 is a subset of S1. And this particular one is going to give the expected active fraction. It's not going to give the entire distribution. Okay, so let's consider this using the single stage Watts model. So the main idea is I pick a node at random, and I calculate its probability of becoming active, and this will give the active fraction of active nodes. Where this tree-based theory comes in is that once I pick this node at random, I want to say that it's okay for me, that it's not horrible for me to not worry about other things that might have fed in. And so locally tree-like is going to say, it's at least reasonably okay for me to not worry about the fact that I'm ignoring this. That's why that's needed intuitively in the theory. And then you say, okay, what are the chances I become active on the next time step? And you can write down either a continuous or a discrete version of this. So this one is a discrete version that I've written here, but you can write down the other as well. So I have a seed. I could already be active, and I might be initially inactive and become active from my children down here who are active, right? I'm either active now, or somebody causes me to become active. And so then there's some chances, and we do the counting, and that's where this comes from. Okay, so I just want to give you the intuition. I don't think going through the whole counting and details of why the factors are exactly what they are is that terribly great. But remember, this is giving a probability of becoming active, and so that's why writing the response function is nice, because you get this for a few different dynamical processes. And again, I'm stealing slides from this technically steals 2 different slides from my postdoc. Okay, so I'll show you a little bit more, and then I'll do the interlude. All right, so we've got the degree distribution, we've got the initially active nodes, we define this auxiliary variable, we compute the expected fractions at a time step n, and then this will also certainly work for these and a few others. Okay, so go to interlude. I try to advance the slide, it lets me do it, finally. So yeah, the interlude was longer than I thought because my PowerPoint's deciding to give me headaches at the moment. There we go. Right. That's longer interlude. Am I on the right slide now? Good. It's a longer interlude than I had in mind. Maybe I shouldn't have, that's my punishment for putting that slide in there. Okay, so locally tree-like approximation. So our paper, which we published in PRE, and we the title was influenced by Freeman Dyson and so on. We had a bit of a battle with the editors over the title of the paper, which lasted longer than I would have liked, and we got our way when they eventually either forgot about it or decided that they were not going to fight me anymore and had not interacted with people like me before. But this does break the official title policy of physical review, for whatever it's worth. The main result of this paper is that the basic type of the tree-based theory I've discussed, so the transition probabilities assume that I have this parent node that's only receiving influence from its children, right? So it's tree-based in that sense. You can get really accurate results. So it's an empirical type of thing with many networks that we tried, even with networks with very large clustering and high value clustering coefficient. If I have lots of small loops, I am nowhere near locally tree-like. In particular, think of a Facebook network. I have lots of small loops. Tree-based theories for many of these things work on Facebook networks. It is not locally tree-like at all. But the analytical result, like from the type of derivation I showed you before, partial derivation, of expected fraction of neighbors, works on that. Therefore, there must be some sort of other theory that has a different set of hypotheses, that is somewhat weaker, that gives me the same analytical result. So we have not derived such a theory, but that's an open problem that maybe some of you will be interested in. Somehow, there's more to it than what's it. When we wrote this paper and also the sequel paper about mean field theory, when we were telling people about it, the basic reaction we had was, oh, this is already completely solved. And it's kind of fun to say, really, how do you explain this? Anyway, so hopefully we don't have the full explanation yet.
Since you're mentioning fun facts, I was a little perplexed as to why you were attributing this quote from Wigner to Dyson.
Because I'm an idiot. Sorry. That was me. Thank you for correction. That was me. That was my memory not working properly.
The unreasonable.
The unreasonable memory. This is
natural science.
Yeah. I remembered the paper and I was wrong about it. Well, I normally know it. I forgot I'm not globally wrong. Is that okay? I'm locally wrong. But yes, you are correct. Sorry about that. All right. So the thing that we found is that it tends to work well when the mean internode distance is sufficiently small. So you can phrase it as it tends. So I say it tends to work well because I don't have a mathematical statement of this. So if a small world is sufficiently small. So I would love to see a more precise version of that with actual mathematics. And the types of results would be like the expected fraction of infected nodes at equilibrium, or the size of the largest connected component in percolation, or things of that sort. And then another way, if you want to make locally tree-like a little bit more mathematical, if you take the number of nodes goes to infinity, you want cycles to have zero measure. And if you're going to compute something from, so the clustering coefficient would have to go to 0 and then goes to infinity. And if you want a finite n, which for our numerics we're going to have, you want to somehow have small cycles, although what small means is going to be hard for me to do that. Okay, so an example, but when it works and when it does not work. So I'm taking the Watts model, I'm putting it on the Oklahoma network. I'm going to suppose that my thresholds are Gaussian distributed with a mean mu and a standard deviation sigma. So the mu is on this axis, and I have managed to cut off the numbers on the axis, which is rather unfortunate. Sorry about that, and I don't remember what they were. Anyway, this is the mean, and the standard deviation is 0.04 on the left, so it's still tightly peaked. And then I have effectively a uniform, or I do have a uniform threshold on the right. And then I've got the numerics. I've got a theory that says I fix the degree distribution and shuffle everything else and do a calculation like what I showed before. There is a somewhat more intricate theory that says I fix both the degree distribution and the degree-degree correlations, and I otherwise shuffle everything. So in general, this black solid curve, the black solid curve is actually blue, and apparently my eyes are lying to me as well. Okay, I switched blue and black when I did this sort of colored form of dyslexia. This is blue solid curve. Is this kind of theory. So if I have the uniform threshold, if I have the same threshold, it's failing when the transition occurs. This is the expected fraction of infected neighbors. And if I have the threshold with some spread, it's working beautifully. And this is a network which has a very high clustering and is definitively not locally tree-like in the definition I gave. One possible resolution that's been suggested to me, which I think is at least reasonable, is that if you squint a little bit, it has cycles such that if you squint a little bit, you can make it effectively locally tree-like. But so Michael Mahoney suggested that to me as a possible resolution to this in terms of the networks on which this thing is unreasonably effective. Another thing that one can look at is mean field theories, which you can loosely think of various ways of assuming a form of being well mixed. So for example, you might say that every node of degree k experiences the same thing, and the only difference between what a node experiences on the right-hand side would be whether it has degree k or degree k prime. And they're typically derived under the following assumptions. You typically, and I say typically because not all of them are going to behave are going to satisfy all these. Absence of local clustering, so locally tree-like in a sense like what I described. Absence of modularity, namely, if I have two different degree k nodes, it is somehow reasonable for me to think of them as behaving the same way. And then absence of dynamical correlations. So if I think of the state of node I and I think of the state of one of its neighbors, I want to treat that as independent when I update node I. I can relax this, so pair approximations are one way to relax it. So pair approximations would be, I would consider all possible pairs of nodes at once. So if I develop that type of theory, I have a higher dimensional dynamical system, but one which is still easier than just doing stochastic simulations of the original system. I want to contrast this with structural correlations, where things like the degree-degree correlation, the homophily, would be a structural correlation. Okay, so let's go back to our regular program. Hopefully this slide will give me less trouble than the interlude. And so we can write down an analytical approximation for the multi-stage case. And it behaves with the same principles in terms of writing it down, but you have, the formulas just look worse. And you have to write down both one for the first response function to become S1 active and for the second response functions, but you can go through the same machinery, and it will give you, when it gives you something reasonable, it will do so for the same reasons. There will be more opportunities for it to fail, and it's going to actually fail in interesting ways. And I've given you some hints. We'll see if I gave them the right way. But anyway, let's look at the time evolution. Okay, so let's suppose we now have, instead of degree 4 and 24, let's suppose we have degree 4 and degree 5, all nodes with the identical threshold. We've already seen the example where having the identical threshold can cause some problems. And so we're going to plot this on the x-axis will be the bonus influence of being S2 active. And so we can get this. And then you can separate it for degree 4 and degree 5. And the simulations and the theory, are, at least in this example, are working nicely. You can also look at the final you can also look at, say, an error-to-Shreni random graph, so we can try another graph. In this case, again, all identical thresholds mean degree 5, and you can do the same sorts of things. If you want to smooth things out a bit, you can then take the same thresholds before and put now a distribution on the thresholds, and that by itself will not necessarily kill the theoretical prediction. You can still get a nice match. And you'll notice the lines are there, but you don't even they're right on top of each other. You don't even see them. Okay. Now I want to tell you interesting ways that it fails. I think sometimes the most interesting parts of papers are the parts that I don't understand yet. They become less interesting when I understand them. Okay, so interesting way it fails. For one thing, we are using monotonic dynamics, and monotonic dynamics are a very small subset of the dynamics that are there. But let's just concentrate on when these particular monotonic dynamics will fail. So one of them is related to what's sometimes called the June bug effect. So this comes from, I think it was a factory. I'll get this history wrong too, probably even more wrong than the other history, where in June there was someone in a factory who was sort of spreading some rumor of being sick, and then eventually came around to believing his own rumor. This is a gross oversimplification of even what my memory is telling me. Anyway, in this thing, think of it as believing one's own gossip. So there's an S1 active node called J, who influences neighbors who are S not nodes to become S1 active. But by virtue of those S not active nodes becoming S1 active, this S1 active node then experiences enough back peer influence to become S2 active. Okay, and so this is a dynamical correlation. This is assumed not to occur in the theory that we developed. So this is not taken into account in the theory that we used. And so what can end up happening is that the final fraction of S2 active nodes will be correct, but then the theory is going to underestimate the correct result in terms of when it actually occurs. And so we can construct networks for when it happens. So that's one effect that can occur where one would have to make the theory better to do it. The other one, in the paper we call segregation by state, but I decided last night that it's more like two people trying to figure out who should hang up on the phone first. Where node J has a threshold that's high enough to become S2 active, as long as all its neighbors are S1 active. But then one of those neighbors, at least, cannot become S1 active unless this first node becomes S2 active. So if they could both change at the same time, they would. But if they can't, they won't. So this is also dynamical correlation. So again, the final fractions are correct, but the theory is going to overestimate when things actually change, because the theory does not use dynamical correlations. Okay. Another thing that we've done, using the same types of things but a fancier random graph model, now let's suppose you have different modules somehow. You can think of the different modules either as different circles of friends, or you could think of the different modules as different types of social media. And we have these different modules such that the homophily level, the degree-to-degree correlations, are different in the different social circles. So what you can do is that you can have another random graph ensemble that's going to, this thing should be a lowercase I, by the way, that's going to allow a node that is in module I and has degree k to be connected with some probability to a node in module I prime with degree k prime. And so you can go and do similar types of monotonic dynamics on those kinds of networks. And then here, the stuff that's novel is the random graph ensemble, and then you can actually do something with this somewhat intricate ensemble. And we have one paper where we play around with that. Same types of ideas. One that starts building on some of those ideas, but that starts getting more into data. There was a paper from my collaborators, JP Onella and Felix Reed-Sojas, that came out in PNAS in 2010, and they have data from Facebook from about 6 weeks in 2007 of people adopting different applications. So every hour you sort of have the rank, not just the rank order, but also the number of adoptions of each application during that hour, and they have this for something like 6 weeks. No network structure in the data they have. And what they did in their paper is that they just did a bunch of data analysis in various ways, very cool data analysis actually, to try to look at things from a perspective with phase transitions and so on. And at some point, my collaborator James Gleeson noticed a certain scaling, a power scaling of 1.5 power, and there are some models that he was familiar with that can produce that. And so one of the questions that we started asking was whether those models, first of all, whether those models can actually be used on this data. Second, whether from the perspective of forward modeling, those models are plausible for this type of application in the first place. And in particular, there's some models from Bentley that we were using and adapting a little bit. And so what we have now, and we don't have this quite on the archive yet, so we've got a generative model that we have actually a couple different families of generative models. If we only look at the equilibrium dynamics, they all match beautifully from the perspective of just statistical physics, power law type matching. But if you look at the time dependence, you can now distinguish between some of them matching better than others. And so it's an example that I like because of the fact that the equilibrium dynamics cannot distinguish between various possibilities, and the time dynamics can do so very cleanly. Now, the possibility that works for the best of us could still be completely wrong, right? Because there could be something we didn't consider that's actually much better. But it's a plausible model, at least at the toy level, and other seemingly plausible models work only at the equilibrium and not at the time dependence. And so this model is a copying model. We were considering both originally local information and global information. Global information in the form of, say, a top 10 list where I see, these people adopted Pirates versus Ninjas, which is very high on the app list back then, by the way, in case you were wondering. You look at a top 10 list versus a local, I see my friends downloading or starting to use this app, and so I use it as well, right? So social influence versus something else, right? So it gets at the question that we've been trying to think about, or one of the questions we've been trying to think about. So one of them that includes a long memory window that somehow allows, if my friends adopted it yesterday or 2 days ago, or I don't remember the exact window time we ended up being good, is that we then, if you have a long memory window, that actually ended up being important for this in terms of having the match on the time dynamics and not just on the equilibrium. Whether that's an artifact of the data we have, and who knows. But that was the local information and that feature were the ones that, at least in the class of models we considered, were the ones that were working out nicely. Okay, so let me give some conclusions.
I have a
Yeah, absolutely.
about that.
Should I go back to that slide?
Yeah. I thought you said at some point that you were able to distinguish between the local information and the global.
Okay, so let me phrase. So let me give a more precise statement, and maybe this will answer the question. Because I could have said it wrong. What we have is a We have a term that says I have a linear combination of local and global, and I'm going to have half of my choice coming from, or sorry, I'm going to have mu fraction of my choice coming from local, and mu fraction of my choice coming from global. And the mu that worked best in terms of having the time dependence fit was one where the local contribution was almost 1. That's a more precise version of what I was saying, and I suspect the way I phrased it before probably occluded what I had in mind. Does that answer your question?
Yes, it does. I mean, I was actually very curious what the nature of the data you had. That people, if you had access to whether they were looking at the global list.
I do not have that access. The data we have is actually rather sparse. The data we have literally is, every hour we have a list of how many of these different things were adopted. So we have no idea what they were doing. So that's why it becomes very hard for me to say. I can make the sort of neutral statement of this matched better, and one of the points that we're making, and this is actually why we're submitting it to a fancy journal, is that there's a lot of stuff out there where they don't bother distinguishing between the equilibrium and having things match, and seeing many things matching equilibrium, whereas only some of them might still match when you have time dependence. And this data, although it's sparse, at least is rich enough to address it, and it happened to have a clean answer in this case. Whether the mechanism we found translates to anything else in real life, I hope it does, but I can't say that with any confidence. Yeah.
So that app adoption data, I think one of the main things I was characterizing at the time was sort of this ring of fire trope, which is that apps are being adopted and then sort of abandoned, which is sort of consistent with an SIR model as opposed to SIS. And I'm wondering if you have any sort of temporal data or modeling approaches to distinguishing the idea of resilience.
So the data that we have does not indicate how often people subsequently use it.
Okay.
So we would not be able to do this with that data. From the perspective of that data, somebody could never use it again, and they've turned from 0 to 1. You're correct?
You still have an observation of the frontier.
Yeah, we have the observation of the frontier. So the plan for that paper, actually, that paper was originally supposed to be on the archive 6 months ago, but one of my collaborators has a relative who's been sick, and so there was sort of real life distractions preventing us from finishing. And so because I'm having a sabbatical in Palo Alto, one of the things I very much wanted to do was to email Facebook data team and say, this is what we've done with that data so far. Can we design an experiment with modern different data, but that allows us to go deeper? But I've not been showing them this yet, just because I haven't had the paper in a polished enough form where I've been comfortable to show it to them. And now that I've been there for a month, and I'm going to be there for 2.5 more months, maybe we'll finish it early enough that I can reasonably do that. I hope so, but I know they're also very busy. So, but yeah, I mean there are sort of dreams dancing in my head of doing a more sophisticated version of this. But I feel like we have to show that we can do something reasonable with a smaller version to convince them to do it in the first. It's like the discussion we had before lunch, right? I have to show some level of success with a more difficult data to convince them to let me play with your stuff, right? Oh, whoops, sorry. Well, let me just go back to you probably read the conclusions, but I want to go over it anyway, if it will let me. So, for some reason it doesn't want me to scroll, which I don't understand. All right, so I won't bother going to the slide. That's okay. All right, so main conclusions. One is that modeling social influence is an excellent playground for applied mathematics. Mathematics and the social sciences, I think, is very exciting, and I think that applied mathematicians can come up with, at least in principle, experimentally testable things, as what has been true, for a longer period of time in other fields, and I think it's a good challenge to take up. And a lot of these models are tractable, so you really can do some math with them. Okay. There are subtleties regarding when tree-based and mean field theories are valid, and so although I think it's treated sometimes in the literature as if there's nothing left to figure out for those, I would completely disagree with that. And our papers haven't figured them out, but we've tried to point out little corners where, okay, look, there's actually more understanding to get. And so that's an interesting project more on the mathematical side. I'd love to see, what is the right sort of sharp set of hypotheses that will let me have that result of mean infected neighbors eventually being true. That's something I would like to see. And then we've also introduced an analytically tractable model of multi-stage complex contagions, but there's a lot more work. There's a lot more work to do. So, as usual with my talks, this is one of the things that sort of changed in my life after I got a good job. I don't need to impress you. I care more that you're interested in the problem than you're interested in what I did with the problem. Right? That's because then you can build on stuff regardless of what you think of mine. So I hope that you found this interesting. And if you say, oh, but you should have done it this way, and I say, good, go try it. Let's see what happens. All right, so that's it.
Questions?
Stunned silence. No, go ahead.
So I guess I was curious because you have the level A tree-like if the analytic is more effective than maybe it should seem. I was curious if you looked at maybe instead of full numerical simulations, just doing kind of like very local numeric simulation on the more complicated and confounding issues with multi-stage on just around neighborhoods.
Well, we did that to try to get our heads around of why the analytics were failing, but not at the level of trying to actually develop new approximations. The paper, at some point you just say, this is the story in the paper and I don't want to tell too many stories and we have to put a bow on it and that's for the next paper. I agree one could do that. We only did it to the extent of just trying to figure out the couple failings that were occur and figuring out those two particular failings was not something that just took us a day to do. It was one of those, why is this consistently overestimating it? Types of thing. And we wanted to at least have some notion of what would cause it to overestimate. But yeah, you're right. Mm-hmm.
Hi. This is a similar question about seeking intuition, and it relates to the remark that I think you attributed to Mahoney, that maybe if once...
Well, I attribute it to him because that was a personal conversation between him and me. That attribution, I know I'm right because I actually had that conversation.
No, I'm not questioning the source of the attribution.
I feel bad about the other mess up that I made, that's all.
More whether or not you've thought of any ways to test that. And as I understood it, just for those who mightn't have written it down as I did, that squinting at a network with small cycles was maybe equivalent to somehow renormalizing the network.
So let me comment on that. So the squinting is phrasing that Michael likes to use because essentially you possibly could think of it as renormalizing, but if I have there's something, for example, called tree width, right? So I could, for example, try to formalize this through low tree width if I wanted to bring in some graph theory ideas. But I might imagine that I have a bunch of cliques that are done this way. So when I say squinting, and yes, you can think of it like a renormalization if you want, at least at an empirical level. If I zoom out, this is a node, this is a node, this is a node, it suddenly becomes a tree, whereas the actual network is decidedly not a tree. So yes, in principle, one could do it that way. If I were going to do that, I would start by looking at notions like tree width and path width and so on that are notions that are already defined and see if by those criteria that I would then develop a theory that says, I don't want it to be locally tree-like, but I want some renormalized version of the network to be locally tree. This conversation that I had with Michael is something that I had a couple weeks ago because he's my host at Stanford. So if I ever go back to that particular corner of this problem, which I might, that would more or less be the first thing I would try. I'm not confident how quickly it would get it to work, but his answer is at least plausible, so it's worth checking to see if you can really answer it that way. Sorry, this is a really bad picture. Anyway, I got the point across.
Any other questions? Oh.
So what would be your dream data set?
Oh, my dream data set. I dream a lot. I have a lot of dream data sets. I don't know if I really have one. I dream so much that I already have more data than time, to be honest. What I'd like to...
I mean, what are you trying, what would you...
What I'd like to be able to... What I'd like to be able to do with Facebook is to actually design an experiment that's run on Facebook, which is some of the stuff that they've done in their collaborations with James Fowler and so on. And to actually design one with social influence, I'd have to think about how to design it properly, but I'd want to do it as a designed experiment, not just collect data after the fact and sort of reconstitute it from its original purpose. That doesn't say exactly how I would design it. I think I would have to think about that a lot more, but it would definitely be something designed rather than just given to me and reconstituted. It's an incomplete answer. It's a complete answer to a question that's slightly different from the one you asked. But
I mean, the one I'm curious about is specifically when you raise this question, you have a way of modeling the, the local versus global. That's not the full generality of the problem.
No, it's not. No, it's not. No, it's not.
But I'm just curious if
Oh.
you have ideas to try
Right.
to start disentangling.
I don't think I have concrete ideas. I sort of have vague ideas of like types of features I would want. So I would want to. So one of the reasons I would want to do this with Facebook is that they have enough of a cross section of different things that I would want a sort of ensemble of different experiments, so that I would worry less about something weird about a particular choice. So that's one of the features that I would want. But I would more or less want that with almost any experiment that I would design. I'd have to think a lot more than I have about actually doing it, because I've not yet had sort of an opportunity come to me in terms of it being feasible of getting a data set that would let me even do that. And so as a result, I haven't thought about it to the deep level. I mean, I know that in terms of the conversations I've had with Facebook data team in the past, and I haven't had, I think the last one was actually quite a while ago now, they really work closely to make sure that they design the experiment well beforehand, before they let you use the data these days. The Facebook data that I showed you that I used, there's two sets. There's one that was so what Felix and JP did is that they were, I'm blanking out on the word now, but they were actually extracting the data during a period of time with setting up programs. The 2005 Facebook data I got when Facebook was young and stupid. Facebook version of A-Rod for you baseball fans. But they didn't know at the time how much their data was worth, and at the time, if you had a social connection to someone on Facebook, which I did, you could say, could I have data? And they would say yes. I mean, this world is long gone. So now you really have to work with them and say, all right, what do I want to do? And how do I design this experiment? But some of the stuff that Facebook data team does is that they, so for example, you've probably seen a recent, or some of you have seen a recent change where when you add a friend, they say, do you know this person offline? Right, it's a very recent change. I know for a fact that data team is trying to figure out, how do you go from offline friendships to online friendships. There's various works from people like Dana Boyd who've said, oh, online friendships just come from offline friendships. But you can test that, and she did it by hand with I think about 1,000 different nodes on both MySpace and Facebook in 2007. It's also possibly true that the answer might have been different in 2007 and 2013. So I know that they do experiments like this in terms of some of the features that they add and all that. So anyway, various random thoughts from conversations I've had with them, But yeah, I would try to. But I specifically would want to do it as a designed experiment and not just collecting a ball of data and trying to reconstitute it, because I think the latter would be very hard to be able to disentangle. It's possible to be clever that way, but I think it's not going to be easy for this kind of problem. But
all right, let's thank Mason again, and there's food over there.